Okay, so today we are moving on to actually both sections 1 and section 3 of chapter 12, because they're both pretty short. Section 1 especially is short because the counting principle is very easy to cover, so I decided to kind of combine it with the probability section. So let's talk about some definitions first with probability and some of these things. An outcome is just the result of a single trial. Sample space is the set of all possible outcomes. An event is one or more outcomes of a trial. So if you're flipping a coin, an event would be getting heads, or heads would be the outcome. And so if you flipped it, what you actually get, if you got heads, that would be the event. So the outcome is what you could get. Event is getting the heads or the tails. So then we have independent events. It's a series of trials where the outcome of one event, that should be an event, does not affect the results of the other trials. So again, flipping the coin, rolling a die, those are all independent events, because when you roll it, that does not affect what you're going to get the next time you roll the dice. Or if you flip a coin, that's not going to, just because you got heads the first time doesn't mean you're automatically going to get tails the second time. So it says the sandwich cart offers customers a choice of hamburger, chicken, or fish on either a plain or sesame seed bun. How many different combinations of meat in a bun are possible? So when we look at this, we have hamburger, we have chicken, and we have fish. Then you can make kind of a tree diagram to do this. You could say on the hamburger, you can have a plain or a sesame seed bun. On the chicken, you could have it on a plain or a sesame seed bun. And the fish, you could have on a plain or a sesame seed bun. A result of 1, 2, 3, 4, 5, 6 different choices of sandwich. So what do we notice about how else could we have gotten there that way? Another way of doing that would be to use the fundamental counting principle. The fundamental counting principle says if you have m different ways of one event and n different ways for a different event, all you do is multiply the two numbers and you get that number of events. So we had 3 types of meat, or 3 types of sandwiches with 2 different types of bread. 3 times 2 gets us 6. So it says many answering machines allow owners to call home and get their messages by entering a 3-digit code. How many codes are possible? Now, the assumption here is that you could repeat numbers. So we have 3 digits. 1, 2, 3 digits. We have 10 digits, 0 through 9 for the first one, 10 digits for the second, and 10 digits for the third. Our fundamental counting principle tells us we multiply. So there are 1,000 different choices for codes that you could put into your machine. So not unreasonable that you could sit there and try to figure out someone's answering machine code. However, a lot of people don't have answering machines anymore, if you guys even know what that is. I don't know, some of you might still have answering machines, I'm not sure. Alright, dependent events. So this is where, like for drawing cards, when you draw a card, if you don't return it, that changes the outcome of the next draw, because now there's one less card to choose from. So dependent events, the outcome of one event does indeed affect the outcome of another event. So Charlita wants to take 6 different classes next year. Assuming that each class is offered each period, how many different schedules could she have? So looking at this, we have 6 different periods. Okay? So periods 1, 2, 3, 4, 5, 6. There are 6 different classes she could take here. However, for the next one, there's one less class because she's filled one of them here. So now there's only 5 options for the second. And there are 4 options for the third, 3 options for the fourth, 2 options, and then finally she just has one last option. So, how many different schedules could she have? 6 times 5 is 30, times 4 is 120, times 3 is 360, times 2 is 720 different schedules. Now obviously it's really not likely that every class is offered every period, but to make this problem simple, that's the way it happens. Alright, so the homework for this piece of the lesson is going to be 8 through 17. So it is on your calendar on page 687. So that's the homework for this section. I'm going to switch over to the other PowerPoint. We're going to go ahead and jump into section 3. So you should have a section 3 set of notes. So I did these two separately instead of combining them into one. So a few more definitions, this time specifically with probability. Probability is a ratio that measures the chances of the event occurring. So again, a ratio being a fraction of some kind. So we're looking at numerator and denominator. And the success and failure is pretty obvious. Success, that's what you want to happen. Failure, anything other than what you want to happen. So, probability of success and failure. If an event can succeed in S number of ways and fail in F number of ways, then the probability of success, which I'm calling P of S, the probability of success, and the probability of failure, P of F, are as follows. So if you look down at the bottom, the probability of success is just the S plus F should be the total number of different things that could happen. So really you're looking at just what you want to have happen over the total number, or anything else over the total number. So it's really just those two different fractions. So again, not super complex here, just defining just so everyone's on the same page. Alright, so here's an example that they have for probability. It says Monifa has a collection of 32 CDs. 18 are R&B and 14 are rap. As she is leaving for a trip, she randomly chooses 6 CDs to take with her. What is the probability that she selects 3 R&B and 3 rap? So she wants 3 and 3. She has 18 and 14 of the 2. So what we're looking at is we can use the fundamental theorem of counting principle, but in order for us to really figure this out, we need to go back to what we did in section 2 and look at combinations. So this is kind of like that same hand of card thing that we did when we had 3 clubs and 2 diamonds. We want to figure out what's the number of ways that I could have 18 R&B CDs and choose 3 of them, and then we want to figure out of 14 rap and choosing 3 of those. So we want to figure out how many different ways there are for each of those, and then using the fundamental theorem of counting principle, figure out the total number of ways. So this would be 18 factorial all over 18 minus 3 times 3 factorial, we'll get a number for that. And then 14 factorial all over 14 minus 3 factorial times 3 factorial. And we'll get a number for that. So, let's take a quick minute. So we have 18 choosing 3, and that gives us 816 different ways of choosing her R&B. And then we're going to have 14 choosing 3, and that gives us 364. So the total number of ways would then be 816 times 364. And that is going to be 297,024 from choosing 3 of each. So that's our total number of successes. Our total for both success and failure would be the combination of 32 CDs choosing 6. And that's going to be a very large number at 906 192. So 906,192 different options for choosing just 6 CDs at random. So the probability of choosing 3 and 3 would be 297,024 divided by 906,192, which is approximately 0.32777. So it was rounded off at 0.3278. So about a 33% chance, so a third of a chance of her getting exactly what she wants there. Alright, so here's a rather large example. So Ramon has 5 books on the floor, 1 for each of his classes: Algebra 2, Chemistry, English, Spanish, and History. Ramon is going to put the books on a shelf. If he picks the books up at random and places them in a row on the same shelf, what's the probability that his English, Spanish, and Algebra 2 books will be the leftmost books on the shelf, but not necessarily in that order? So you're probably thinking, who cares? What am I going to figure this out for? We don't really need to know. However, what we do want to figure out is there's 5 total books. So what we would do is we'd figure out, we'd kind of divide the 2 groups of them. So we'd have they want English, Spanish, and Algebra 2. So we have English, Spanish, and Algebra 2 books over here. And then we'd have, what do we have left? History and Chemistry. So we need to figure out the arrangements of these and the arrangements of these for the numerator. That's our success rate. So we'd have the permutation of 3 choosing 3 at a time and the permutation of 2 choosing 2. But that's really just going to end up being 3 factorial and 2 factorial. 3 factorial is 3 times 2 times 1, which is 6, and 2 factorial is just 2. So that's the number of different ways that we can arrange each set of books. And then beyond that, our total number of books is just the permutation, because again, order matters here, of 5 choosing 5, which is 5 factorial. 5 times 4 is 20, times 3 is 60, times 2 is 120 different ways. So this is 12. So then our total probability here would be 12 out of 120, which would then be 1/10 or a 10% chance of him putting them in that particular order. Alright, just a few more definitions here. A random variable is a variable whose value is the numerical outcome of a random event. So that's more, it's more of a technicality thing here. It's just a variable whose numerical outcome of a random event. And the probability distribution. This is something that you kind of get into once you get further into probability, but it's a function that maps the sample space to the probabilities of the outcomes in the sample space. So again, a sample space being all the possible outcomes, and then to the probabilities of those outcomes. So if you look, I have an example of this, where this would be your sample space. So you have 2 dice that you're rolling, and these are all the different numbers, these are all the different sums you could get, and the probabilities of those sums. So this would be a probability distribution because you map the sum. What are the chances of getting 2? It's 1 out of 36. Chances of summing the 2 numbers to 3 is 1 out of 18, so on and so forth. So then using that table, there's a few questions they ask you. First they ask you, use the table to determine which outcome is most likely. Then they ask, what's its probability? Well, that one would be, if you look at which one has the smallest denominator, the biggest fraction, that would be 7. So the sum of 7 is the most likely, and the probability of getting a 7 is 1/6. which outcome or outcomes is least likely? Well, that would be either getting a 2 or a 12. And the probability of 2 is the same as getting the probability of a 12, which is 1 out of 36. There's only one way to get a 2 and one way to get a 12. That's either double 1s or double 6s. Then they want us to use the table to find the probability of the sum of 3. So the probability of the sum equaling 3, if you look at your table, you're looking at the bottom number, and it's going to be 1/18. Well, what other sum has the same? That's also the same probability as the sum of 11. Because there's two ways to get a 3. First dice is 1 and the second dice is 2, or the other way around, where the first one is 2 and the second one is 1. Probability of getting 11 is the same way, either a 5 and a 6 or a 6 and 11. Alright, so one more example kind of using the same idea of probability here. Alright, it says an administrative assistant has 4 blue file folders, 3 red folders, and 3 yellow folders. Each folder contains different information, so 2 folders of the same color should be viewed as being different. She puts the file folders randomly in a box to be taken to a meeting. Find each probability. So, what's the probability of 4 blue, 3 red, 3 yellow in that order? So again, order here matters. So what do you want to do? So we're going to look at this the same way we looked at the other ones. By the probability of success, we'll do each one individually. We have the permutation of 4 choose 4. Then we have the permutation of 3 choose 3. Then the permutation again of 3 choose 3. And that's our success. We multiply each of those. So I'll just tell you now the total of all of those. Well, we'll do each one individually. So if you do 4 permutation 4, you get 24. Then each of these are 6. And when you multiply all those together, the probability of getting them in that order, you do 24 times 6 times 6, you should get 864. Then you do the probability of just choosing 12 at random. So you do the permutation of 12 choose 12, which is going to give us, 10 choose 10. I keep wanting to think there's 12 folders. There's 10. Of 10 choose 10 is 3628800. So this is your success, this is your failure. When you divide that out, and you do 864 divided by 3628800, you end up with 1 out of 4200. And you can divide that out, and you get a very small decimal of 0.000238. So there's less than a 1% chance that happens. Now, the first two being blue and the last two, the first two being blue and the last two being blue, you'd have a permutation of 2 choose 2, which is just 2. Then you have 6 folders in the middle. We don't care what order they're in. So you just have the probability of 6 choosing 6, and then at the other end of it, you have the 2 again. So the permutation of getting 6 is 720. So again, 720 divided by 4, 720 times 4 is 2880. So then our total here would be 2880 divided by that same total, because you're, again, choosing 10 folders. And when I divide that out, you get a very small fraction of 0.000794. So a little higher, but again, way less than a 1% chance of that happening. Alright. Your homework for that section is also on the calendar. That's going to be the one that's on page 700 or 701. So you'll be doing both of those assignments for this particular section.